right, let's take a look at exercise 12.1, which is our chapter 12 problem set. So thermistors are used to measure the temperature of bodies. Thermistors are based on materials change in resistance with temperature. To measure temperature, manufacturers provide you with a temperature versus resistance calibration curve. If you measure resistance, you can find the temperature. A manufacturer of thermistors makes several observations with a thermistor, which are given at the end of the problem. Determine the temperature corresponding to 754.8 ohms. So we're given the data of temperature versus resistance, and so we're asked to determine the temperature for a given resistance. Great. So we're given R. So I'm going to I'll use interp1 to find my solution. I'll create a vector of R. I'll create a vector of T. Then when I use interp1, I can think of R as being my independent variable because I'm going to specify the value of R and try and estimate T at that value. All right, so I'm going to start by creating a new script. Okay, I'll just do it in a script since we're just asked for the resistance. Okay, and I'm going to start by creating a vector of R. So I have 1101, 911.3, 636, and 451.1. So then I have T. And so T is 25.113. 30.131. 40.120. And 50.128. Okay, cool. And so let me make a note. This is exercise 12.1. So here's my resistance in ohms. Here's my temperature in degrees C. Okay. All right, cool. Now, just in the interest of problem solving, so I'm going to interpolate. And actually, let me first just solve it using interpolation, and then let's try and play around and think of what might be the best way to interpolate would be. So I want to determine temperature when our resistance is equal to 754.8 ohms. Okay, so I'm going to interpolate using interp1, and so I'm going to call this RL. So if I use linear interpolation, and I'll just compare. So my command would just look like interp1. Okay, my independent variable is going to be R. Right, I'm going to try and specify the value of R and get T at that value. So this could be R comma T. Actually, I'll call this T linear. R comma T, and I'm going to specify. And let me say, let me just store R naught to something. 754.8, and I'm going to specify R naught. So that'll be linear interpolation. If I want to use cubic interpolation, it's interp1. Interp1, R comma T comma R naught, specify P chip. Okay, and so in its bare essence, there it is. When I use linear interpolation, I estimate 35.8095 degrees C. Cubic is 35.3385. Okay, so in terms of which one do I use, linear or cubic? All right, so one way is I could try both of them for a given problem and try and assess the difference and see if that's within whatever precision I need for a given problem. When we solve diffq using ODE45 at a large amount of data, and so when I have large amounts of data at fine spacing between data points, it often doesn't make much of a difference. It's here when I only have a limited data set that it can often make a difference. What I'm going to do here is I want to, actually, I can do it afterwards. Okay. So let's make a plot and compare linear versus cubic, right, to get an idea of which would be best. So I'm going to open up figure 1. Okay, I'm going to start by plotting my data. And so I'm going to plot r comma t, and I'm going to plot that as black circles. Next, I'm going to do the linear approximation. I'll call it, or linear interpolation. Okay, and so what I'm going to do here, and this is all completely unnecessary, but I'm going to create a vector of, say, Ri, points where I'll make my resistances where I would interpolate. I'm going to create a vector. I'll use linspace, and I'm going to go from R1, okay, to R end. And I'll just make it 100 data points. Okay, and then I am going to, so the corresponding temperatures I would get TL from linear interpolation would be interp1, and it's going to be R comma T, and I'll estimate the values at all of those Ri. The temperature I'd get from cubic interpolation, R comma T comma Ri comma P chip. And then I'm going to plot and see what they look like. So now I'll plot, we call T Ri versus TL, and I'll plot that as a black line. And then I'll plot Ri versus TC, and this will be a blue line, I guess. Okay. So that didn't work because I spelled interp1 wrong in one of these commands. So it says on line 20, and it looks like I actually have an extra R command in here. That's what it is. It's R comma T. So it looks like one, oh, that's an L, not a 1. Bah. Okay, cool. All right, so graphically, what do I have? So the black circles, oh, I need to change those colors. So those are black circles. Let me make this a red line. So the black circles are the original reference data. Red would be what I would get from linear interpolation. Blue is what I would get from cubic interpolation, right? And so it looks like maybe there is some slight curvature to this data, so maybe cubic is a better representation, but it's ultimately just a judgment call, right, in terms of thinking about what I would use. And just for fun, let me just even add to this. I'm going to plot, let me plot the point I just calculated. So I will do R0, comma TL, and so I'm going to do a red star. Then I'm going to plot R0 versus TC, right? Because we had our value from linear interpolation and cubic. And I'm just going to plot these as stars on the graph, just so you can look at them. So here's where I'm estimating my temperature, right? And here's the value from cubic interpolation, and there's linear interpolation, right? And the difference between the two. But that's it for problem 2, right? I'm going to create a vector of my resistances and temperatures. I'm going to think of R as being my independent variable. Okay, I'm going to specify a value of R and try and estimate the value of T at that point. And here I'm using linear interpolation, which is default, and then also looking at cubic interpolation, so piecewise, cubic, Hermite, interpolating polynomial. The only purpose of generating a plot here is, one, we can look at the data and just try and make a judgment call based on it, of whether or not we think linear or cubic interpolation would be a better fit. But that's it, right? And you could easily take this and wrap it up into a function where maybe an input is R naught, the resistance for what you want to try, where you want to try and estimate the temperature. You could even make the type of interpolation an input. All right, so linear, okay, it's not required, okay, but I could specify that it's linear interpolation, which is the default. All right, gives me the same answer. And so you could easily even make this string an input to the function. So the function could have an input of R naught, could also have an input of the type of interpolation. The sky is the limit. But that's it for linear interpolation. We looked at a couple of other cool examples in class, so I hope that helps. Let me know if you have any questions.